Well, I'll get back to that in a moment. We can again express xt as integrals. And once again, this first integral will be familiar to you. This is the integral of calculus. That's the Riemann integral. Namely, integrating the constant from 0 to t, you get the value alpha t. That's simple. This is the one where, once again, it's a stochastic integral, not any of the familiar integrals you're likely to have encountered, and it requires a new definition that Ito introduced. But we can, with that new definition, actually recover x at the value t by integrating this process in the appropriate way. The properties of this process are, as we've seen, they're normally distributed. We get a drift, and we get the Brownian term, all scaled so that we can make one of these processes have whatever mean and variance we want, namely by picking alpha and sigma. As I was beginning to say a moment ago, arithmetic Brownian motion might be an appropriate process for many applications, but it's not a good process for stock prices because, first of all, there's nothing to prevent xt from becoming negative. Indeed, more than there's nothing preventing it from becoming negative, the normal distribution wants to become negative. It's distributed on the entire real line, so no matter how large the mean of this distribution gets, there will always be a non-zero probability of negative stock prices. In fact, when the time interval is short, the probability of negative prices will be close to a half. So this is not an appropriate stock price process. The other problem as a stock price process is we have the mean and the variance terms in this process only depend on time. They don't actually depend on how big x is. And many people will think that this is inappropriate for stock prices because if you do an empirical analysis of stock prices and you look at periods of low stock prices and periods of high stock prices, it tends to be the case that the mean change, the change in the stock price will be on average bigger and be more variable when stock prices are high than they are when stock prices are low. Intuitively, the mean change in stock prices is proportional to the stock price. And intuitively, the variability of stock prices is proportional to the stock price. So this process has the property that it has fixed mean and variance that does not depend on whether stock prices are high, low, or negative. The mean and the variance are fixed. And these criticisms are going to be eliminated when we turn to geometric Brownian motion later. Another variation on Brownian motion is called an Ornstein-Uhlenbeck process. This is one we will come up with again in the final chapter on interest rate models. And it has, first of all, you see the variability term looks like arithmetic Brownian motion. It's just a sigma times Brownian. So that's providing the variability. But notice that an Ornstein-Uhlenbeck process has an interesting drift formula. And this is what's called mean reverting. That if you look at the drift in this series, the expected change, first of all, it says that the change, just like additive Brownian motion, is normally distributed. But now notice that the mean of that distribution varies with x. The variance is still fixed. So the variance of this Ornstein-Uhlenbeck process is the same as the variance of arithmetic Brownian motion. But notice that the mean changes with x of t. And what is that? It's called mean reversion. And the reason is, imagine for the moment that xt is smaller than a. Usually lambda is a positive number in these processes. So when xt is smaller than a minus x is a positive number, and you have positive drift. So when xt is smaller than a, the drift is up toward a. Imagine, on the other hand, that xt is bigger than a. Well, then this is a negative term, and the drift is negative. So this is a mean reversion process, which is very popular in interest rate models, which is saying that a is the value at which x is always moving. If it gets above a, it starts to move toward it, and if it gets below, it starts to move up toward it. And lambda gives you the speed of the reversion. It's sometimes called the reversion parameter. But if lambda is big, close to 1, of course, if lambda is equal to 1, the reversion happens in one step. If lambda is large, like 0.8, mean reversion happens faster than if it's equal to 0.2. As with arithmetic Brownian motion, x can again become negative in this process, and that's a problem in the application of this process to interest rates. You have interest rate models that can produce negative rates.